Welcome back to the next editions of Learning Mathematics Through Example. Today we're going to focus on A-level mathematics, particularly on topics mechanics. Right? We can look at the topics down here, mechanics. Um, in this case, there are many topics under mechanics. We will focus on the first topic, which is kinematic. All right. Now let's get going. um, Now, before we start with any mechanics questions, it's always best to recapture some of the fundamentals that we need for this topic, kinematics. Now, kinematics is all about motion, and then in this topic, the motion is restricted to straight line. And then most probably in our example here, we try to restrict the motion um, to a constant acceleration. Right? So there are a few fundamentals we need to set up before we can work with any mechanics problem. Right? Now, firstly is the graph. Right? Let's try to understand um, two different type of graphs that may appear in the exam in this case, right? So the first graph is, I'm going to draw it down here. Right, now the first graph is displacement or distance against time. Right, so I just choose one of these, displacement. Unit for displacement is meter, and then displacement is a vector quantity. Therefore, it has both magnitude and direction. Right? So don't forget that. There are like a few features that we can actually obtain from this graph displacement against time. But here we will only concentrate on some of the important features, right? Now, take for instance, we have a simple graph that look like this. I'll take for instance in this case, and then something like this. Right? Now, how do we describe the motion of this object based on the graph given here, right? So maybe let's try to put some value onto this so that it's easier for us to analyze the motion here. Okay, right. Now in this case, we can see that the object initially start off from the origin or a specific location, and then it will move to a certain or to a new location after 5 seconds. So the new locations A, maybe I'll label this as A. The new location A is about 10 meter away from the initial location O, or the origin here. And then next, the object rest. In this case, it rests for, let's assume that it rests for 2 seconds between A and B. So we can see that this section representing stationary condition, because the displacement or the distance does not change from 5 seconds to 7 seconds. And then from B to C, we can see that the displacement, or in this case, the displacement would change from 10 meter to 0 within 3 seconds. So what is going on here? Most probably, the object would return to the original position where it first started. Right. So this is the graph that represent these types of straight line motion. Now, how does it look like in the simplest physical world, for instance? All right, now I'll try to illustrate this with a simple diagram here. So we say that the object starts from O, and then it would travel to A somewhere here. Let's assume that position A is here. Right. This position A is about 10 meter from where it starts from. And then it will stay there for 2 seconds, from 5 to 7 seconds. That is between A and B, because position does not change. And then after 7 seconds, it would actually return. We can see that the displacement is 0. So most probably it's going to return back here to 0. So we can see that the displacement is 0. Because displacement is a vector quantity, it simply means how far is C from where you started from. So C is 0 meter from O. Right. So this is a very simple linear motion of an object. So the features you need to remember regarding this graph would be the gradient of this graph, displacement against time. The gradient of this graph represent velocity. It represents velocity. If the title represent distance against time, then the gradient would represent speed. That's the only difference, right? But bear in mind, the area under the graph is insignificant with relations to kinematic in this case. So the main thing you need to remember about the graph displacement against time or distance against time is the gradient of the graph. So the gradient OA is uniform, meaning that the object is moving at a constant velocity in this case. The velocity between AB is 0 because the gradient is 0. And then the velocity for BC is represented by this gradient here, gradient of BC. We know that gradient of BC is negative. Now, negative velocity actually indicate, so you have to remember this, indicate change in direction. So you can see that from this diagram, there is a change in direction. So this is from B to C. Now, I hope that that would actually refresh your memory on the graph displacement against time or distance against time. Now, next, the second graph that we need to focus on is velocity against time graph. So let me label this first. Velocity. Unit for velocity is meter per second. Time is second here. Now let's assume that the motion of this graph would look something like this. Okay. Let's use the same setting then. Okay, so this one is 20 for instance. This is 5. This is 10. This is maybe 15 for instance. Right. Now in this case, based on the graph, how can we describe the motion of this object? Okay. Now we can see that it starts off from rest because velocity was 0 initially, and then the velocity increases from 0 meter per second to 20 meter per second under 5 seconds. Right? Because the velocity is increasing, therefore we can say that the object must be accelerating. Now the gradient of the graph velocity against time graph represent acceleration. This is the first feature that we need to remember. represent acceleration. Okay? And then we can see that as it moves from O to A, it is moving at a constant acceleration. When you move from A to B, the object is not um, it's not stationary in this case, uh, which is a bit different from the graph displacement against time graph. For this graph velocity against time graph, the motion between AB is the object is moving at a constant velocity. Constant velocity means constant speed in the same direction here. And then when it moves from B to C, now we can see that it decelerates. It decelerates from B to C at a constant deceleration here. So the gradient for BC also represent acceleration, but in this case it represents negative acceleration. So here let me make a remark. Negative acceleration, also known as deceleration. Okay, so be very mindful with the terminology that you are using. And then lastly, area. If you want to know how far the object has moved throughout the journey here, now the area under the graph represent the displacement or represent distance in this case, right? Now, how do I find the area under the graph? Now, you don't have to use any special fancy formula here. All you need to do is observe the graph. It basically consists of a regular geometrical shape. So you can use the formula for area of a regular geometrical shape to evaluate the area under the graph, and then therefore we can conclude that area under the graph for velocity time graph represent displacement or distance. Okay, now let me show you how does it look like physically in this case. Now let me draw that. So initially it starts from O, is accelerating in these directions to A. Its velocity at A is 20 meter per second here. So it has accelerated from 0 to 20 meter per second within 5 seconds. And then after that, it maintained its velocity 20 meter per second for another 5 seconds here until it reached position B. And then lastly, maybe due to the fact that it's almost reaching its destination, it will need to slow down by maybe applying a brake, for instance. Therefore, the object is decelerating within another 5 seconds to reach the position C there. Right. Now here you can see that there is no change in the direction here. There is no change in direction because the velocity are all positive in this case. So this is sort of the final destinations here. Right? Now I hope that is clear. Now in terms of acceleration, just a remark. Acceleration, how do I find the acceleration OA, for instance? Accelerations between OA is given by rise over run, which is the height of this triangle over the width of this triangle. So for OA, in this case, we have a height of 20 and then a width of 5 there. Therefore, it gives us a 4 meter per second square. That's a unit measurement for accelerations there. All right. So I hope that is clear to all of you. The features of the graph that you are supposed or you are given in this case. So do pay attention to the type of graph that is given to you, the unit system, before you attempt any mechanics question. Right? Now, lastly, the Suvet equation. Yeah, this equation is only valid provided all the acceleration is uniform, right? Now, some of the Suvet equations, we don't really need to memorize it. It's given in the data booklet itself. So here I'll try to write down some of them so that we can refer to later on. Right now, take for instance, we have V equal to U plus AT. This is one of them. And then you also have displacement UT plus half AT square. And then of course you also have V square equal to U square plus 2AS. Don't forget, the last one is the most important one because you guys are taking AS right now. Okay, hopefully you are clear where the AS actually come from. The A stands for acceleration, the S stands for displacement or distance in this case. Alright, so these are some of the formula A, B, C that are most frequently in use. Of course, in your data booklet, they give you another one, which is quite similar to B. Right? Okay, so I hope that is clear. Just preempt with the knowledge that you need to know under this topic kinematic before we move on to applying this knowledge to solve mechanics problem. Okay, now I hope you guys are ready for the first question. Let's look at that. I'll leave this information at the side here. Yeah, whenever I run out of space, I may remove this, right? Okay, let's look at the question in this case. We are given a train travels from A to B, right? A distance of 20 kilometer or 20,000 meters in this case. The journey take about 1,000 seconds. The journey is being divided into 3 stages. In the first stage, the train starts from rest at A and accelerate uniformly until it reaches the speed of v meter per second. Now, in the second stage, the train travels at a constant speed v meter per second for 600 seconds. During the third stage of the journey, the train decelerates uniformly, coming to rest at B. Now, the first question, how are we going to sketch the graph velocity time to represent the motion of the train in this case? Velocity time graph, just to remind ourselves. So if you look at here, velocity time graph is this one here. Okay, now let's get started with this velocity time graph. Now, first of all, velocity time graph, I would have the time here, second, and then I would have velocity here. Make sure you make it a habit to write down the unit measurement in this case. All right. Now it started off from A. Okay, start from rest, and then the whole journey take about 1,000 seconds. Okay, 1,000 seconds. Initially, it start from rest and then accelerate uniformly until you reach the velocity v. So maybe I mark down v here. So it actually accelerate uniformly until you reach a velocity v here. Right. Now the question here is, I have no idea how long does it take for it to accelerate to reach a speed of v here. So I just write down t then. The second stage of the train, it will be moving at a constant velocity v, here, constant velocity v for 600 seconds. For 600 seconds, so which means it will reach t plus 600 because initially it took t seconds to reach that position, and then after that it maintained a constant speed for another 600 seconds. Now, for the last stage of the journey, the train decelerates uniformly. until it come to rest. Come to rest. The only way you can come to rest is, oops, sorry, I did this again. Okay, right. Okay, hold on. All right. Now it actually come to rest after decelerating. So we know that the total journey is 1,000 there. So let me correct the drawing. Now that's how the graph um, that we should be drawing to represent the journey of the train here. So before we end everything, just check through all the features of the graph. Have we represent all the informations required here? Just check here. Yes, we do, right? So basically, you can leave it as it is. This is how the graph would look like in this case. Okay. All right. Now next, number 2, we need to find the value for v there, right? We need to find the value for v. Now in this case, we know that the total journey would take 20,000 meters. Now, just to recap, the total journey is represented by the area under the graph here. So the total journey would be 20,000 meters. Okay, so let's try to use this information, right? So just let me erase this. Okay, too much erase. Let me get a smaller one. Okay, all right. Now we know that the total distance is 20,000. So area under the graph. All right, now the total distance is represented by total area under the graph. Right. Now, getting the area under the graph should not be a problem in this case, right? So we try to work out the area under the graph. Okay. Now, up to how you would like to work out the area under the graph in this case, it's either you can work out area by dividing the total area into a few sections to work out each of the areas, or you can actually use the formula for trapezium, because this is actually a trapezium. You can use a formula for trapezium to find the area under the graph. So the area under the graph is given by half. Now multiply by the sum of the parallel lines. Now we know that the parallel lines are this line and this line here. And then just to recap, this length is 600, and then this length here is 1,000. So therefore we'll put in 600 plus 1,000 here, and then multiply by its height, which is a v. Right, now this is how we find the area under the graph, which represents the total distance traveled. Okay, now before we move on, we might want to simplify this. This is 1,600, so there will be 800 feet. Okay, and then given by this extra information, we know that the total distance traveled is 20,000. Therefore, we can equate this 80,000, sorry, 800 V equal to 20,000. And then by doing a bit of algebra manipulation, we should be able to reach the final conclusion regarding the value B here. So let me see, add 2 there, add 5, okay. So let me check one more time. Okay, sorry, I think I overshoot one decimal there. Okay. All right. Now that should be the speed or the value for v in this case, which is 25 meter per second in this case. Right. Okay, so I hope that is clear for question 1 and 2. Right. As you can see in this problem, you may find that there are a lot of labels here that we did not actually discover, like the T itself. Never mind, we will find out shortly with more informations. Then we can work out the rest of the unknown. For instance, the T here, right? Okay, so I hope that is clear for first section. Right, now the third one. Given that the acceleration of the train during the first stage, which is this part here, is given as 0.15 meter per second square. Now we need to find the distance traveled by the train during the third stage of the journey. So third stage of the journey basically refer to this area under the ground. Okay, this is the area here. Right. So in this case, we will need to know how long does it take for the train to accelerate up to 25 meter per second here. Okay, right. So that's our task here. We need to find out the t's before we can work out this area. Right. Right, now I'm going to erase off any information that's not required. Alright, okay. Then I get a bigger one. Okay, right, let's work out number 3. Now we are given that the acceleration for the first stage, for first stage is given as 0.15 meter per second square. And then the way to work out the acceleration is taking the height of the triangle, which we call rise, and then divided by the run in this case. Therefore, in this case, the rise is v, which we have obtained previously, 25. So I'm going to write down 25 divided by the run, which is t. Therefore, we have this, and then that will show us what do we have here? 103, 500. Five, 3. Let me check whether I'm getting it right. 20 there, 15, 5, 3, 5, 5, 2, 500. Yes, correct. Right. So the time taken to accelerate up to 25 meter per second would be 500 over 3 seconds. 500 over 3 seconds. And then, therefore, at this point, when we have t plus 600, all we need to do is just take this value of t, add up with 600. Right? Okay, so I hope that is clear to this part. Now we still need to find out the area under the graph for the last stage. Okay. Right, now to find that, all we need to do is figure out, in this case we just need to figure out the length for the height of this triangle. We have already found the height of this triangle, which is 25 meter per second in this case. So now we have to figure out what is the width for this triangle. Now the width for this triangle is basically 1000 minus of this value t plus 600, which means is 400 minus this. Let's try to find this out here. Yeah, maybe I'll label this as height, and then this is the width here. So the width of this triangle is given as 1000 subtract off with t plus 600. Yeah, if you subtract all this, then we will get the width there. And then by doing a bit of simplification, we have 400 minus of t. This is the t that we have obtained, which is 500 over 3. Now that would actually give us 750. Hold on, let me, sorry, it's 700. Yeah, it's supposed to be 700. Hold on, just let me clean that up. Okay, so it should be 700 over 3. So just let me check before I finalize the answer. Okay, so it's 700 over 3. So the width here is 700 over 3. Now therefore, we're going to answer the final question here regarding the area under the graph. Find the distance traveled by the train during the third stage. So the distance traveled by the train in the third stage is given as half multiplied by the height and then multiplied by the width in this case. So that is 700 over 3 here. Alright, so we can take our calculator and maybe simplify that. Okay, let me try this out. This one requires a bit of calculation, so this is just let me try this one out here. Okay, too many values there. Okay, that will be at 12.5. Okay, so that would give me. Okay, let me see what we have here. Okay, do we have a decimal number for this? Hold on for a while. The decimal number for this is okay 2917. That's 2917. 2917. Right. So the last section of the journey would take about 2,970 meters. So I hope that is clear. So bear in mind, area under the graph represent displacement or distance, and then the gradient of the graph velocity against time graph represent acceleration or deceleration in this case. Okay, now do help me to check in case any numbers that I calculated wrongly. Do drop a comment. Yeah, for this video, right? I'll be very happy if anyone can spot any errors. So it's a good way to learn in this case, right? Okay, now if you are okay with this, I'm going to move on to the next questions now. Okay, let me clean up all this. All right, second question. Okay. Now, in the second questions, we are given a graph velocity against time again. Let's read through the description. An object P travels from A to B. From A to B in a time 80 seconds. So most probably it's from here to here, A to B, within 80 seconds. The diagram shows that, it shows a graph of velocity against time, where V is the velocity of the particle P at time t after leaving A. Now the graph consists of a straight line segment. In this case, the first part is a straight line for the interval of time between 0 and 10 seconds. So you can see that it is a straight line. And 30 to 80 seconds. So 30 to 80 seconds is also a straight line. And a curved section whose equation is given by this section here. So the curved section is over here. For the domain of time lying between 30 and 10 seconds. Okay, so we are clear on what we are looking at, and then next we are going to find out what is the task that we need to complete here. So the first question is find the maximum velocity of p. Okay, now just by looking at this graph, the maximum velocity of p can be found here. This is the maximum velocity. Okay, most probably the answer will be somewhere in between, right? Somewhere in between 10 to 30 seconds. Right now, that's how the logic should be viewed from. Right? Okay, so the next question is, excuse me for. Next question will be, how are we going to work out the maximum velocity here? Right, there are many methods here. Right, there are many methods we can work out the maximum velocity. Okay, all right. Please hold on for a while. Methods to work out the maximum velocity in this case. We are going to use all the methods that you learned in your pure math, whether it's pure 1 or pure 3, doesn't matter in this case. So the equation for that represent this section of the journey is given by v equal to negative 0.01 t squared plus 0.5 t minus 1 here. Right, we are trying to figure out the maximum from here. Okay, so by using the knowledge from pure 1, we can use traditional methods of completing the square, because the purpose of completing the square is to locate any stationary points, may it be a minimum or maximum in this case. All right, now I'm going to use this strategy to work out the maximum velocity in this case. Later on, after I've done this, I'll show you another approach that we can use. So using completing the square methods, I'm going to write down at the side here how we are going to complete the square here. Right. Okay, we're going to start from here. Firstly, I would actually take out 0.0 and factorize this. Hold on. There's a 2 here, and then divide by, so subtract off. In this case, you will have to have 50 here minus 1. Okay, just to recheck, we have 0.5. Yep, so everything is in context now. If you try to expand this, you should be able to reach this section. Okay, once you are done, we are going to proceed on with our completing the square form. In this case, it will be okay. So here I take a bit of shortcut. I have already square this number here, minus 1. Now the final stage is to re-expand it. So if I re-expand it, I would have obtained this, and then that would be 1, 2 here. So that would be a plus 62.5 there. Did I get that right? Oh, sorry, I think I got it wrong. So just let me correct that. It's supposed to be 6.25. 6.25. Yes, correct. So 6.25. Okay. So divided by 100, 10. Just let me check one more round in case I make any mistake. Okay. Yep. Okay. So 6.25 there. And then don't forget we have minus 1. So from here we have negative 0.01 t minus 25 square, and then we have 5.25. Okay, I have already completed the square in this case for this quadratic equation. And then what can we extract from here? What informations that we can extract from here that can help us to identify the maximum velocity in this case, right? So from here, we can conclude that the velocity, sorry, the velocity is maximum. The velocity is maximum when t is equal to 25 seconds. So we can find that the velocity is maximum at t equal to 25 seconds. But anyway, at time t equal to 25 seconds, what would be the maximum velocity? So maximum velocity is given by this value here. Therefore, the maximum velocity at time t equal to 25 seconds is, it's very clear in this case, is 5.25 meter per second. Now that will be our maximum velocity. Okay? And then we can check whether it makes sense in this case. 25 seconds is within the domain of 10 to 30 here. And then the maximum velocity is found with a value of 5.25 meter per second. All right, now that's how we are going to find maximum velocity using completing the square method. Now, of course, some of you are asking, is there any other methods that we can use? Yes, for sure, right? Now, I'm going to clean this up. I'm going to show you another way to approach this question number 1. Okay, if you are ready, I'm going to clean this up. It's also a good way, a good method to check, though, or an alternative method to check whether what we did before this was accurate, right? Okay. So the second method to obtain the maximum velocity is by using calculus, differentiation in this case. Okay, differentiation. So we are given v equal to this. We are going to obtain dv dt, rate of change in velocity, which indirectly is acceleration. Right? Okay, now I hope that you still remember how to differentiate this. You can treat the t as x. So if t is a x, how do you differentiate x squared in this case? So that would actually give me 0.02t plus 0.5. Now that will be my dv dt, or indirectly is quite similar to dy dx. To find the stationary point, we have to let dv dt equals 0 because the gradient at the maximum velocity is 0 in this case. Therefore, from here, we can figure out when the velocity is maximum by finding out the time here. So that's actually 0.5 divided by 0.02. And then in this case, you can see that is actually 25 seconds. Yep, exactly the same as what we got from the previous completing the square method. Now, once we have found this, we can even verify whether this is a maximum velocity or whether this is a minimum velocity. Of course, based on the diagram, logically speaking, it must be a maximum. But in terms of calculus wise, can we verify that from the algebraic point of view whether this is a maximum or minimum? We can undergo the carry out the second derivative, meaning that you differentiate this one more time. That will give you 0.02, which is actually less than 0. That would confirm our velocity to be maximum. Right? Now we are ready to figure out what will be the maximum velocity at time t equal to 25 seconds. Maximum velocity is given by this value here when the time is 25 seconds. So I'm going to substitute that. plus 0.5, 25 minus a 1. Right now, I'll try my best to see whether I can do it manually without any calculator. So this is 6.25, and then that will be like 12.5. 12.5, yeah. Is let me see, 125, 12.5, yeah. And then minus a 1 there. Now, in this case, let me see what we have. We have negative 7. Okay, negative 7 here. That will be 5.25 meter per second. All right, that actually confirmed our previous finding, which indicate that the maximum velocity is supposed to be 5.25 from completing the square methods. So I would say, hooray! Okay, right. So it's always a good way to find an alternative approach to that same problem as a tool to verify your working. So this is also another method of checking your working. Right? Okay, so I hope that is useful at this point. Finally, we're going to find out the distance AB. How are we going to find out the distance AB? Distance AB is area under the graph. Yeah, area under the graph in this case. Right. Now to find area under the graph, I can work with the first area here, and the next I can work with the next area here. Okay. Now before that, I might need to find out what will be this velocity here, v1, and then what would be the velocity at this point, v2. Okay. To find that out, the only way we can figure it out is by using this equation, because that is the only equations that we have at this point of time. So for B1, I'm going to work out V1. V1, all we need to do is just substitute 10 into this equation here. Okay, I'm going to write that down here. I hope that it's not too messy. Right. At t equal to 10, V1 is given by this equation here, negative 0.01, 10 squared plus 0.5, 10 minus 1 here. So let me see. There's a negative 1 plus a 5 minus a 1 there, and that will give me 3 meter per second. Okay, and then at t equal to, in this case, t equal to 30, v2 is equal to negative 0.01, 30 squared, 0.5, 30 minus 1 there. Let's see what we have here is a 9, and then plus 15 minus a 1 minus a 10, that is a 5 meter per second. So this is 3, this is 5 meter per second, and then the maximum is 5.25. So that makes a lot of sense, and then it does fit in the logic. Right? Now once we are done with this value, we can first of all find out the area under the graph for this section, because this area represents the distance traveled within 10 seconds. So let us find out the distance traveled here, first section here. So I'm going to say that distance. Okay, so distance. Okay, distance S1 first. Okay. How do I find the distance? It's quite direct, which is half times 10, and then multiply by the height, which we already found out, which is 3 in this case. So therefore, we have 15 meters. All right, so that's the first region. The second region is here. Okay, this is a bigger region. This distance is given by, okay, let me just write it down. So distance S2 is given by the same formula here, half multiplied by the width. Don't just copy down 80 here, no. It's the difference between here, which is 50, and then multiply by the height, which we already found out as 5. So that will be a 125 meters there. Just let me check whether it's correct. Yeah, it's 125 there. So now we know that area for first stage is 50 meters. The last stage is 125 there. And now what is left is the area in this region. Okay. This one is tougher because it's not a regular shape that we recognize. Therefore, we have to make use of calculus to find out area underneath that region. Okay, so hold on, just let me clean that up a bit. Okay, we're going to apply calculus methods again to find out the area under this curve. So this area here, I'm going to draw it down here. Distance S3, which is given by the integration between 10 to 30. So from 10 to 30, and then I'm going to integrate this 0.01 t squared plus 0.5 t minus 1 dt. Okay. Now, hopefully you guys still remember how to integrate this. Okay, so that is basically 0.01 over 3 t cubed plus 0.25 t squared minus a t. Now, of course, your calculator is advanced enough to actually help you to calculate this quite easily, I would say. Okay, right? So just let me try this out. What are we getting from here? Okay, just let me get my software and then let me calculate that more easily in this case. Okay, hold on. Just let me make it smaller a bit. Okay, is it moving? Okay, it's not. It's still moving on. Okay, there you have it. Hold on. Just let me get this going there. Now here I need to integrate. Okay, integrate. Okay, let me see. Functions of negative 0.01 x squared. 0.5x minus 1. Okay, let me see what we have. 10 to 30. Okay. So the area for this section, or the distance, is given by 93.3 meter. Okay, I'm not sure. I think it's meter. Okay, in this case, I'll leave it as meter. Right. Okay, so I hope you guys are clear how to find the area under the graph using a regular geometry, and then with the help of calculus if it involves a curve instead of a straight line itself. Therefore, we can conclude the distance AB. So distance, let me write down here, distance, therefore distance AB is the same as 15 meters from here, add up with 125 meters for this region, and then finally for the last region, 93.3. Then if I try to compute this, that would be like 140 there, so 233.3, or approximately 233 meters in total. Okay, so I hope that's clear. Okay, Let me clear everything. The eraser is too small. Let me get a bigger one. Okay, let's see how many more questions we have. Okay, let's go on to third questions now. Let me scroll up a bit more. Okay. Right now we are given again velocity time graph. A woman walks in a straight line. Okay, I'm not sure how straight that is. Let's pretend that it's really straight. I think she's using a meter rule as a guideline, I think. Okay. Now, the woman's velocity t second after passing through a fixed point a on the line is v meter per second. Okay. The graph of v against t consists of 4 straight line segments as shown in the diagram above. The woman is at the point B when t is equal to 60. So that is point B when t is equal to 60 seconds. So I'm going to label this at this point. This is position B. Let me read that one more time. Passing through a fixed point A on the line is V. Okay, it's V. Okay, so pass through that at the point. The woman's velocity t second after passing through a fixed point A on the line is V. Okay, now we are ready. Find the woman's accelerations for the accelerations between time 0 and 30 seconds. Time 0 here and 30 seconds. Now you can see that that is accelerating. Okay. Right. Now to make it a good habit, it's always best to draw a right-angled triangle. Yeah. You guys know why it must be a right-angled triangle, right? Because that is the right approach. Okay, don't forget that. Okay, so we are going to draw a right-angled triangle here. And then by using this right-angled triangle, all I need to work out is the rise for this triangle, which is basically 2.1, the difference between 2.1 and 1.5, which is actually 0.6 meter per second. Right, so that is the difference here, which is a rise. And then I need to get the width. The width in this case is pretty obvious, is 30 seconds. Therefore, to obtain the women's accelerations for t line between 0 and 30 seconds, okay, I'm going to write that down here. For t line between 0 and 30 seconds, acceleration of the woman is equal to rise over run, which is 0.6 meter per second divided by 30 seconds. All right. So in this case, we have 0.02 meter per second square. That will be the acceleration of the woman for this time frame. Now next, we also need to work out the acceleration of the woman between this time frame 30 to 40 seconds, which is this section here. For this section, it's quite easy because it's already a right-angled triangle. So we are on the right track this time. Okay, by looking at this triangle instead, for the time frame between 30 to 40, its acceleration is given as the height is obvious, which is 2.1 meter per second, and then the width itself is difference between 40 and 30. That will be a 10 second. Therefore, we have 0.21 meter per second square. Now in this case, I would like to warn all of you that I make a major error here. If you notice that this line is actually descending. Therefore, don't forget, after you use rise over run, always observe the line itself whether it's increasing or decreasing. Because it's decreasing, therefore, this is a negative acceleration, or sometimes we call this deceleration. Because they don't request for deceleration, then we have to stat the acceleration um, in the form of negative, just to signify that it's slow, the object is slowing down, or in this case, the woman is reducing her speed. Okay, I hope that's clear. Okay, just to check, we are done number one. Now we're going to move on to number two, distant AB. Okay, distant AB. It started off from here, and then the final destination is B here. So what would be the distant line in this case, right? Now, before that, I would like to draw a physical diagram to show how the woman actually walk in a straight line. Okay. Now, initially, this is the okay. I'm going to draw it down here. Up here will be good. Okay, this is start off. She start off from A. Okay, and then let me label this as A, and then she increased her speed to reach B here, for instance. This is B. Okay, she move up to this point, B, reach B, and then after that, when she reached C, she reduced her velocity to 0 when reach C. Okay, and then you can see that the velocity turn to negative. When you turn to negative, and then when you reach at 0, that is what we call as a conditions known as instantaneously at rest. It doesn't mean that it stop moving, but it's some sort of making a U-turn or change direction. So you can see that it's changing direction at C, point C. Therefore, this velocity become negative to indicate that the direction has changed. So now the woman is walking in the opposite direction with respect to where she start from. And then she's going to continue to move until she reach a velocity of negative 2.5 there. Okay, and then after that she will keep on uh, increasing her speed again until she reach here again. Okay, sort of she stopped at point B here. Okay, so now we want to see what is her total distance. Now, of course, I'm not sure whether this point B is exactly the same as point A or not. Okay, now just to prevent a bit of confusion here, I might want to, you can make it shorter or you can make it longer. Doesn't matter because we are not sure where B is. Okay, but we can find out from the graph itself. So let's find that out. The first distance from AB. Okay, I'm going to label the distance AB here. Distance AB is given by the area under the graph, indicated here, red in color. Okay, that is yet another trapezium. So I'm going to use that formula for trapezium here. That is 2.1 plus 1.5. Okay, and then by its height. Okay, so let's see what we have. There is a 3.6, 1.8 by 30. Therefore, you have here 54 meters. Right. So the first distance, traveling from A to B, take her to 54 meters. Now next, as she continue to slow down until she reach C, This region represents the distance between BC. Okay, so I'm going to label this distance BC. Let's try to find out. It's much more easier because it's a triangle. So the height is 2.1, the width is 10. So 10.5 meters. And then next, she changed direction until she reached D, for instance. Maybe use D, for instance. So D would be somewhere here, for instance. This is D. So let's find out what is this distance here, D. Okay, this distance is quite easy. So as CD now, that would be half. The distance between here is 12. Sorry, the length between here is 12, and then the height here is 2.2. Now, because we are interested in the distance, so we don't have to include the negative sign. So 6 is 13.2 meters. So this region is 13.2 meters. And then next, we're going to complete the last section here, which is this region. Okay. This region we can find out quite easily as dB is given by half. The width for this is again is 8. The height 2.2. Just let me check one more round in case. Okay, so that is actually 8.8 meters. And now we can conclude that the total distance AB is given by 54, 10.5, 13.2, and then lastly we have 8.8. And then that would actually give me like, what do we have here? Let me see. 20, 22 is 32.5. So 32.5, that is 86.5. Hopefully my calculation is correct. So do help me to check there. Okay, so there you have it. The total distance between A and B is 86.5 meters there. Okay. Okay, I hope that is clear at this point. Now, the distance AB, and then the last question is total distance walked by the woman itself. Okay, total distance AB. Total distance AB is basically the same as the total distance traveled by the woman. So I would say the last questions here is just to confirm that the total distance traveled by the woman is the same distance as AB, which is 86.5 meters. Okay, as usual, do comment and then drop your comment in case there's any mistake here. Okay, all right. So just now, before we go, you can actually check that. You can check whether B is actually exceeded A or not. Right now, we can see from here A to C. So A to C. So AB is 54, and then BC is 10.5. BC is 10.5. So total distance from here to here is 64.5. 64.5 meters here. And then from C to D is only 13.5. Yeah, BC is 10.5. Therefore, CD is correct. The position is correct because CD has a length of or distance of 13.2 meters. Yes, so this part is actually 13.2. And then finally, there's another 8.8. So if you take 13.2 plus 8.8, that is actually 22. So another 22 meters here. So if you add up 22 here, that will be a 35.2. If you add up here, there will be 35.2. Alright, so 35.2 in total. And then 35.2 in total would be less than A here. But that is just something extra for you to think about. So if you want to correct the actual position for B, the B will be somewhere here. Okay, so if you are interested to know more about these sections, you can do more analysis here, this section, right? Okay, I hope that is clear. I'm gonna clean this up now. I think we still have one more question to go. All right, let me clear this and then I'm gonna move down. I think there's still one more. Oh, two more. Okay, let's look at this. Okay. A car travels in a straight line from A to B, which is 12 kilometers apart. The journey takes about 552 seconds. The car starts from rest at A and accelerate for time t1 second at 0.3 meter per second acceleration, reaching a speed of v meter per second. Okay. Now the car then continues to move at v meter per second for another durations of t2. It then decelerates for t3 second at 1 meter per second square, coming to rest at B. So in this case, we want to sketch how the velocity time graph would look like that can represent the motion of this car. Okay, so let's try this out here. For number one, okay, let me sketch that graph. Okay. So as usual, you must have the label for this. Velocity. Okay, this is meter per second. Yeah, even though there is a unit kilometer here, but I think they're using meter per second, so I'll stick to meter per second here. And then time, which is a second. Okay. Either you use a slash or use a bracket, that's fine. Okay, so the object start to move from rest and then accelerate for t1 until you reach a velocity of v. Okay, velocity of v. So it will look something like this until you reach a velocity of v here after durations of t1. Okay. Now the other extra information I should label at this point is it has an acceleration. I'll use the lowercase a to represent acceleration, 0.3 meter per second square for this line. Okay. And then next, it continue to move at v meter per second for t2 seconds. So it continue to move for t2. Okay, just to clarify, this is actually a horizontal line. It may not look that horizontal at this point. Okay, t2 for t2. Okay, and then finally it decelerate for this t2, if I label it in such a way, is a bit confusing. Just let me clarify this properly. So move for t2. For t2, it means t1 plus t2 here. And then finally, it decelerate. Okay, alright, it's overshoot here. Sorry. So it decelerate for t3 second at 1 meter per second square when it finally come to rest. Okay, so in this case it should be t1 plus t2 plus t3. This is the final locations there. When it comes to rest, after traveling for another t3 second there. If you want to look at these informations from a different perspective, you might just label this as t3. This part here is t2. The width is t2. Okay, that might be helpful in a while. Okay, and then one more informations about this journey here. It has an acceleration of 1 meter per second square. Yeah. So I need to check back if I got everything. Taking the whole journey of 552 seconds. So the whole journey take about 552 seconds. So in this case, instead of writing T1 plus T2 plus T3, I might as well write down the total time taken for the journey. In this case, the total time is 552 seconds. Okay, so I hope that is clear at this point. Right, we have indirectly finished drawing the velocity time graph. Okay. Now bear in mind the accelerations, you do not need to label it in the diagram itself. I purposely label it to remind myself all the informations provided for me so that I will not need to read the instructions one more time. It may slow down the time I need to take to solve the other problem, right? Okay, so now if you are clear with this graph, we are going to work on number 2. Express the total distance traveled in term of v. Total distance traveled in term of v, and show that this quadratic equation is true, and then hence find the value of v. Okay, let's try to work out the total distance in term of v. Okay, in term of v. Right? So total distance, number 2 here. Total distance is represented by the area under the graph of this trapezium. So the area under the graph. Okay, under the graph from 0 to 552 seconds in this case. Now that area is given by half. Let me see here. Half. We know that the total time is 552, and then plus the length here. Okay, so just to check, this length is given by the car then continue to move v meter per second for t2 seconds. So this length here is given by t2, and then finally multiply by v there. Okay, so from here, yeah, I don't think we can proceed anymore. That is the total distance. Okay, so I hope that is clear. And then from here, we know that this total distance is given as 12 kilometer. So therefore, I'm going to work it out here. So I can write down this half 552 plus T2 V is equal to 12,000 meters. Right, 12,000 meters there. 12,000 meters in this case, right? And then just let me check there. Yeah, that's what we have. But as you can see, if I do it this way, it does not bring me anywhere, because the first instruction indicate that I need to find the total distance traveled in term of v. Yeah, in term of v. That is the questions there. Right? So never mind, we can leave it here. It might be useful in a while. Now next, what other informations do I have? Yeah, like in the exam under pressure, we have to make use of all the informations that we have. So here we can see that we have acceleration. This acceleration A is given by v divided by t1. And then this acceleration is equal to 0.3 meter per second. Therefore, we can write down t1 is actually v divided by 0.3. Okay. So here I just leave it as, let me see here, is 10 over 3. Yeah, it's 10 over 3 v, that's t1. And then we are also given acceleration of a equal to 1 meter per second for the last stage of the journey. Now in this case we can write down this as a equal to v divided by t3 divided by t3, which is the same as 1. And then here we can state that t3 is actually equal to a v. So this is a v. Right. T1 is 10 over 3v here. Okay. And then one more information we know is total time is actually equal to 552 seconds. And then this total time is basically given by T1 plus T2 plus T3. And then that should be equal to 552 seconds. So what do I have for T1? My T1 is 10 over 3v. My T2 is the one that I have no idea. T3 is a v. And then from here, I can work out my T2 quite easily. In this case, that is 552 minus of 13v over 3. Okay, that's how I get my T2. Okay. So once I found my T2, I can use this information back here to find the total distance traveled in terms of v. So in this case, I can write down my total distance will be 552 plus with T2, which is 552 minus 13v over 3 multiplied by v. If you like, you can simplify as, what do we have here? We have half 1,104 minus 13v over 3, and then multiply by v. Okay, now that will be the total distance in meters. I hope it's clear. Okay, right. So once that is clear, I will be using this information here, the total distance, and then we know that the total distance is equal to, it's very clear here. Now you can see where this piece of information is very useful. We know that this total distance is equal to 12,000 meters. The only thing you need to be very careful of is the unit. Okay. Now let me clean up this little section here. Alright, now we're going to work with these equations now. Total distance is equal to 12,000. We have already described this in terms of v. Therefore, I can write this as half 1104 minus 13v over 3. v equal to 12,000. Okay, so we are almost there. Well, if you want to simplify the whole thing, you can actually multiply by 6 both sides if you want. So you multiply by 6 there, so that will be let me see, what do we have here. Okay, so maybe let me try to simplify it so that it's not confusing for some of you. So 552 minus 13v over 6, sorry, there's a v here, it's v squared equal to 12,000. Okay, this is what we have. You expand that, and then next, to get rid of this 6 here, okay, So we can multiply everything by 6. So therefore we have like 33 1 2v minus 13v square equal to 72,000 here. Then rearranging, we have 13v square minus 3312v and then plus 7,000 sorry, 7,000, 72,000 equal to 0. And then therefore, yes, we have managed to prove that it satisfies this quadratic equation. And hence, find the value for v in this case. So all you need to do is just solve this quadratic equation. Okay. All right. So just let me clean this up. Just let me check what we have there. So just let me clean this up. Okay. Let us see whether we can actually factorize this. Let me get my software here so that maybe it's easier to work with. Okay. Let me see what we have. X squared here minus of 3312x plus 72,123. Okay, just let me check whether I got it right. 72. All right. Okay. Okay. So we have two velocity here. We managed to find we managed to find v as 24 or v as 231. 231 here. Right? So just let me check whether I got that correct. 13v and 3312, 72,000. Yes. So there are two solutions here. So there are two solutions for this equation. Okay, just let me write it down. So it's v equal to 24 or 231. Therefore, based on your calculator, for instance, the solutions to this solutions will be v equal to 24 meter per second or v equal to 231 meter per second. So there are two answers here. You can always try to see whether you actually fit in the description. Of course, at the end of the day, usually for me, I would like to check, even though I got that from my software itself. So I can try using 24 first. Okay, if this one start with 24, for instance, and then therefore my T1 will be 80. Okay, my T1 will be 80. My T3 will be 24 here. So that will be, if you check that from 24, that will be a 5 to 8. Yeah, 5 to 8 here. So another 24, 552. And then that is, yeah, that's what we have. Okay, so far. So if I like to check there, just let me check everything. So let's use this to find the total distance, whether the total distance is actually equal to. Let me use S to represent the total distance. It's given by half multiplied by 24. Here I just multiply by the height first, and then take the sum of the two parallel lines, which is 552, and then add up with this difference here. So we have like 4, what do you have here? 4, 6. Is it 448? Yeah, 448. 448. Just let me check whether it's 448. 448 is 5 to 8. Yes, correct. Okay, so that's what we have. So we have 12. Here we have like, let me see, 10, 10, 9, 10. So that is actually 12 kilometer, which is good. Then next, you can always check using V equal to 231. No? So this is for V equal to 24. Now we're going to check for V equal to 231 meter per second. Okay, let's check whether it makes sense in this case. Just let me clean up the numbers there so that we can work with 231. So let's assume that this time we have, 231 instead. Okay, and then we know that this is 231, so 231 here. 231, we have the 321. So 321 here. Yeah, we have 321 there. And then what else we have here? Let me see. 721, 7. So 77. So is it 77? Yeah, 77 times 10. So 770. Did I get that right? Just let me check one more time. 77 multiplied by 10 is 770. Okay. Right now, you can see that here there is a contradiction to the time that we are working on. So because of this, this solution here cannot be accepted, even though quadratic wise it does satisfy the equations, but in terms of logic itself, this velocity does not fit in this context. So we will have to you will have to sort of omit these solutions here. So we will say we have to reject these solutions. So the only answer, only value of V that we are interested in is 24 meter per second. Okay, so it's always good to check. Drop me a comment in case you have other thoughts on this. Okay, so we are done. Now we are going to move to the last question. I think it's the last question. Okay, let's see what do we have here. Okay, last one. Okay, this I think is the last one. Yep. Okay, this is the last one. Is the okay pretty lengthy in this case. Okay, let's see what do we have here. Okay. All right. Now we are given a graph of velocity time graph. Now this diagram shows the velocity time graph for a particle p which travels on a straight line AB. Where v is the velocity of p at time t. The graph consists of 5, 1, 2, 3, 4, 5, 5 straight line segments. The particle starts from rest at t equal to 0 at a point x on the line between A and B. At a point x on the line between A and B, and move towards A. Okay, move towards A. So let me try to draw out another diagram just to show us the physical context of what we are looking at here. So we have AB here. We have X somewhere here. And then it was stated that this particle move way. Let me see. The particle comes to rest at A. The particle start from rest at t equal to 0 at a point x here between line A and B and move towards A. So it move towards A, this direction. Now the particle come to rest at A at t equal to 2.5. So here. But based on the graph itself, you can see that it come and rest somewhere here, 2.5. So this is position A. Okay. And then it's quite obvious that there's a change in direction. There's a change in direction here, from here to here. Let's label this as AB here. There's a change in direction. And then it will move in this direction. Okay. And then after that, it will maintain, excuse me, it will maintain a constant velocity. Okay. And then finally, it would decelerate until it reach its destination at t equal to 14.5 seconds. Okay, so generally that's how it looked like. Okay, let's try to interpret further. Number one, given that the distance xa is here, is 4 meter. So this is 4 meter. This xa, 4 meter. Find the greatest speed reached by p during this stage of motion between x and a. Between x and a, the maximum greatest speed reached by p. So the greatest speed reached by p is here. This is the greatest speed. Okay, that is the greatest speed reached by the particle. And then we know that this area under the graph represent the distance traveled, which is 4 meters here. Okay, using all this information, I can work out the distance xa. So write down the distance xa is given by 4 meter. Okay, this distance is calculated using this formula here, half multiplied by 2.5 multiplied by the width and the height. Okay, multiplied by the height. Okay, and the height I will label as V max, which is the maximum speed reach in this case. That will be equal to 4. Okay, so I hope that is clear there. Therefore, V max will be 8. In this case, will be 8 divided by 2.5 there. Right. So let me see what do we have here. We have 5, 16. Okay. So 3.2 meter per second. Okay. Just let me check one round in case I calculated wrongly. It's 8 divided by 2.5. Okay, so it's 3.2. So therefore, the greatest speed reached by B during this stage is 3.2 meter per second. Okay, so I hope that's clear. Now the second stage. In the second stage, P starts from rest at A. When T is equal to 2.5, yeah, and move towards B. Now it changed direction. It moved towards B. The distance AB from A to B here is 48. Okay, just let me extend that up to here, for instance, is 48 meters. Now the particle takes about 12 seconds to travel from A to B. So it takes about 12 seconds to travel from A to B. So this is like, okay, this is not B now. I think I made a mistake here. I just simply label there. The B is actually here. So the whole journey take about 12 seconds. Okay. Now for the first 2 seconds, of this stage, P accelerate at 3 meter per second square, reaching a velocity of V. So at this stage here, okay. So the velocity, the acceleration. Acceleration at this point is given as 3 meter per second square. Right. How can we make use of these accelerations to obtain the value for B? So we are at this question here. Okay. Given that acceleration, I will rewrite this. Given that the acceleration, we are on questions 2 now. Acceleration is given as 3 meter per second square. Acceleration is given as v divided by the rise. The rise divided by the run. The run is 2 seconds here. Therefore, we found that the v is actually 6 meter per second. Now, next, the value of t at which p starts to decelerate. The value of t at which p start to decelerate during this stage. So this t, the value of t at which the particle starts to decelerate. Okay. So we need to figure this out. Now, before we can do that, we have to make use of the informations that we have about the total distance traveled. We know that the total distance traveled from A to B, which is represented as an area under the graph. Okay, so I'm going to use that. Number 3, total distance given as 48 meters. And then this total distance is evaluated using this formula here. That is the sum of the parallel length. This is a 12 plus this length here. So I just label this as this length is given as t minus 4.5. Hold on. Is t minus 4.5. Okay, and then multiply by v, which is 6. Then that will yield 48. Okay, from here, I try to simplify that. Let me see. We have 316 here. That is actually 87.5 plus t is equal to 16 here. Yeah, equal to 16 there. Therefore, the time t that we are looking at is, let me see, is it 8.5? So 8.5, yeah, 8.5 seconds. So the value of t at which p start to decelerate during this stage is 8.5 seconds. Okay, so I hope that's clear. Now, next one, let's see, the last one. The deceleration of p immediately before it reaches b. Well, that will be very, very obvious at this point of time. So deceleration, number 4. I will try to calculate the acceleration in this case. Acceleration from here to here, acceleration is equal to a rise over run. So the rise is a v again, which is a 6. And then the run is here, the difference between 14.5 and 8.5 there, which is actually a 6 second. And that would actually give me a 1 meter per second square. And then before you conclude, you have to check the geometrical shape in this case because it's descending. Therefore, don't forget to put in a negative there. So the acceleration is negative 1 meter per second square. But because they want the answer in using deceleration, then therefore we can conclude that deceleration is equal to 1 meter per second square. But always make it a habit to write down acceleration in terms of negative to remind yourself of the ascending or descending nature of the acceleration or deceleration. Okay, now that concludes our sessions on mechanics. I hope this will be a useful reference to your studies. Right? Do drop a comment if you need some more explanation on any questions that you're interested to work on. All right. So until I see you again, uh, happy studying, and then enjoy learning math, like how you would enjoy a piece of cheesecake. Right? Okay. Thank you very much.